Hey Ramblers, this video covers chapter 12.2 in our textbook and deals with the surface area of pyramids. Now pyramids have both a lateral area and a base area, like prisms. But because they're pyramids and they only have one base, the formula for total area is a little different. So after watching this video, you should learn the formulas and be able to calculate the lateral area of a pyramid and the total area of the pyramid. We're going to start out the video talking about some of the parts of a pyramid, which maybe remind you of some of the material we covered in chapter 9.8. Then we'll move on and talk a little bit about some of the problems that come up in the section through the tutorials. Alright, thanks for watching. Take careful notes, especially for any formulas that you should be putting on a formula page, and I hope this helps. When dealing with the surface area of a pyramid, we first have to remind ourselves of some of the parts of a pyramid. And these are terms that came up in our exploration of pyramids in chapter 9.8. If you want to refer back to that video, it might be a good idea. Let's look at the parts of a pyramid, and we'll notice that P, where the lateral faces meet, is the vertex. Running from the vertex down to each of the corners of the base, or each of the vertices of the base, are lateral edges. Lateral edges are where the lateral faces meet. They meet at lateral edges. Where a lateral face meets the base, we have a base edge. And where at the very bottom of a pyramid is the base. Pyramids are named by the shape of the base. So this would be a square, or perhaps it's a rectangular base pyramid. Most of the pyramids that we deal with in this book will be regular pyramids, but not all. So it's very important that you confirm that before moving on in some of the problems that we'll be doing in the exercises. Regular pyramids have a regular polygon as its base, which of course provides its name, and also all the sides, or the faces, are isosceles triangles, which means all the lateral edges are congruent. So a regular polygon has a regular polygon as its base and congruent lateral edges. That's going to bring in the 1/2 apothem times perimeter formula for some of the different bases when we need to find the total area. Okay, let's take a look at another feature or another part of pyramids that are important, and those are the base diagonals. They'll come in handy. They intersect in a regular pyramid, typically at the place where the pyramid's altitude hits the base. But let's move on, take one thing at a time. The pyramid's slant height is the height of a lateral face. So what that means is each of the lateral faces is a triangle. Well, the pyramid's slant height stretches from the vertex down to the midpoint of a base in a regular pyramid, and it meets that base edge at 90 degrees because, of course, it is the height of that triangular face, so of course it's going to meet the base at 90 degrees. Now the slant height is what we use when we're calculating the lateral area and the total area of the pyramid. Now the lateral area of a pyramid is 1/2 the perimeter of the base times the slant height. Now this is only for regular pyramids. Let me state that again. The 1/2 perimeter base times the slant height is only for regular pyramids. If it's a rectangular pyramid or a non-regular pyramid, you have to calculate the area of each face. You can't use this 1/2 perimeter of the base shortcut that we used, similar to what we used with prisms. Total area equals whatever you calculated for the lateral area plus the area of one base, because in a pyramid, of course, we only have one base. Okay, let's take a look at one other part of a pyramid that's going to become useful in this chapter, but not in this section, and that's going to be the pyramid's altitude. The altitude stretches from the vertex 90 degrees, or I'm sorry, to the base, and it meets the base at 90 degrees. For a regular pyramid, this will be where many of the diagonals will meet, It's also going to be the center of the pyramid if the pyramid is a regular pyramid. Once again, the altitude of the pyramid forms a 90-degree angle with the base, and the foot of the altitude is the center of the base if the pyramid is regular. All right, we're going to come back and use altitude for volume. What you want to use for area is the slant height. Okay, now there's a couple of helpful, not a couple, there's more than a couple. There are some helpful triangles to use when calculating the area, because we'll need to sometimes find the slant height or find the altitude. The first I'd like to point out is one that's made up of the slant height and the altitude of the pyramid. And as you can see it here, it's kind of in the middle of the pyramid, stretching from the altitude through the base, and that would be an apothem in a regular pyramid, to the midpoint of a base edge, and then the slant height makes up the hypotenuse. Okay, let's take a look at the base edge, the lateral edge and altitude triangle. As you can see, that's kind of in the also in the middle, stretching from the center out to one of the vertices of the base, and then the hypotenuse is one of the lateral edges of the pyramid. Another valuable triangle is from the slant height as one leg, half of the base is another leg, and then the lateral edge makes up the hypotenuse. And finally, we'll be using a triangle on the base, which is made up of the apothem, half of a side, and half of the diagonal, making up the hypotenuse. So let's see how we use some of these triangles and altitudes and slant heights as we solve some of the problems. All right, Ramblers, thanks for watching. Number 10 on page 568 is probably the toughest of these problems in this section. And since it doesn't have a diagram, I figured this would be the one to do for the tutorial. It tells us that each lateral edge of a regular square pyramid is 3. So the first thing I can take away from that is that the base is a square pyramid. And it tells us that the height of the pyramid is 1. Now be careful, that's not the slant height. When they refer to the height, they're talking about the altitude, as we saw in the video. So let's draw our picture. Okay, so I've drawn my pyramid, and you can see that I labeled the lateral edge 3 and the altitude 1. I've also labeled the points. Now, I admit that my drawing's not perfect. It's difficult to see PD, which is the lateral edge in the back. But the rest of the pieces are pretty simple. And the trick now is to use the triangles that I showed you earlier in the video to find the different pieces they need. Or we need. A asks us for the measure of the diagonal of the base. Well, that's clearly going to be QC is going to be involved in that. So I'm going to use triangle QPC, with P being the vertex. PQ is my altitude, so that's 1. PC is my lateral edge, so that's 3. And then, since the altitude meets the base at right angles, I have a right triangle. And so, by the Pythagorean theorem, QC is going to be the square root of 8, or 2 root 2. Now, if I double that to get the entire length of the diagonal, I'll get my answer 2 times 2 root 2, which is, of course, 4 root 2. Okay, let's take a look at letter B. That asks for the pyramid's slant height. Well, if I know that the half of the base is 2 root 2, then that makes a 45, 45, 90 triangle on the base. So that means that the QR is going to be 2. So since I already know QP, I'm going to use triangle PQR, where PQ is 1, QR is the new side I just found, 2, and since that makes a right angle there, I have another right triangle where I'm trying to find PR. PR, by the Pythagorean theorem, will be square root of 5, just as it is in the answer. Okay, for letter C, it asks us to find the area of the base. Well, since QR is 2, I know that that's half of the length of the base, so the entire base from A to B will be 4. 4 squared, since it's a square-based pyramid, is going to be the area. So the area is 16. And finally, in part D, they ask us for the pyramid's lateral area. Lateral area, since this is a regular pyramid, will equal 1/2 the perimeter of the base times the slant height. And the slant height we found was √5. So that will equal half of 16, which is 8, √5. Okay, Ramblers, that's really the trick to these, is, I think, to identify which triangle you need, to redraw the triangles I did in part A and B, and plug in the values you know, and use Pythagorean theorem. Okay, hope this tutorial helped you.